Thanks, Rahul, for the welcome. And yeah, as Rahul said, I spent some of the best years of my life, my career, right here in the Behl, in MLab, and in town, all the same places you all go to. It's always exciting to return to the same university. And although I touch and go fast, really, it's really a pleasure to be here and this time to come and discuss some of the research that I've been able to do in the past few years. Speaking of which, let me try to justify my clickbait title a little bit. So, these days, there's a lot of resurgence of solving robotics using foundation models and data-driven models and pushing towards artificial intelligence. And a lot of my research also is about robotics and AI, but with a particular emphasis on safety of the real physical systems. That's sort of been the critical focus of my group's work. But I'm a little bit skeptical when people say that AGI is right around the corner, because in my view, most of us would agree that driving is a pretty intelligent task, human level, and requires human level intelligence and skill. Yet we don't really have artificial general driving intelligence yet. So artificial general intelligence for many things is maybe a little bit far off than many would claim. So this talk is going to be about my work, a little bit of a potpourri, a mix of the research side of what my group has done in this space. Despite decades of research, something is clearly not going according to plan. These cars are getting stuck in traffic. They get frozen when they encounter some unexpected situation, and sometimes they just make the kind of mistakes that no human would make. And so we have to be able to reason why this is the case. So let's start there as the way to have this discussion over the next 40 minutes or so. What is it about autonomous driving which is making it super challenging that we don't have these self-driving cars already driving everywhere? And the answer is very complicated. It's not just a technical reason, but being engineers in this room, I'll today only focus on technical reasons. But believe it or not, once a month, I sit across from lawyers who are trying to figure out liability issues of autonomous driving. So there's non-technical reasons to why we don't have these cars yet. But what is the technical reason? So in a nutshell, here is why it is such a challenging problem. And that problem is one of coverage complexity. Right? So you can think of all of driving as having this very high dimensional space, or operating in a very high dimensional space where the car has to detect all different sorts of objects in the world, which can come in uncountable variations and lighting and poses and combinations of all of them. These objects don't exist in isolation. You also have to figure out all the same objects in all different environments. So it could be low visibility, high visibility, night, day, you name it. Those are some finite sets, but this is extremely high dimensional. The number of things on each axis is beyond any single person's ability to articulate. And you can loosely translate this to the problem of perception, or ability to understand the world around us, represent it in some kind of abstraction. So let's say you solve this, which I think some computer vision people would say we have made the most progress on. This axis is the configuration of how these objects interact with each other over time. So even if you detect everything reliably, the way they interact with each other and the spatio-temporal aspect of what manifests in a traffic situation is, again, such a high dimensional space, which you can loosely map to the problem of motion plan. And so all of self-driving is this game of where you are, how much coverage you have of this box, how well can you perceive, how well can you plan in various kinds of interactions, predictable or unpredictable. And the state of the industry is that they are working in different pockets, operating in different cities, in these bounds, which we call operational design domain, within which you can make some statistical guarantees, but outside of which all bets are off. And that's why driving doesn't generalize as of today. So really, with this phenomenon in mind, I'm going to structure our discussion on what I have done to sort of address some of these problems. I don't have all the answers, but my goal is going to be able to talk to you about the problems and share some of our early thinking and progress videos. So in particular, we'll talk about a very fundamental question: how do you measure if autonomous vehicle is safe? This ought to be something we have to measure if we want to make any claims about safety versus humans. Then I will talk about it's not enough to just measure Do we have any ideas of how we can improve autonomous vehicle safety? And some out of the box thinking here can help us. Then I will then talk about how do you handle these uncertain situations, that long axis, which you can never really enumerate. So can you do something to enhance the likelihood that when you encounter unexpected situations, you behave safely? And finally, after doing all of this, you still have to drive the car. So I will talk about how do you drive the car safely within limits? How do you model the physics of these cars? Now, all these four are very deep research thrusts. And what I have done is for 3 of them, we'll do some 30,000 flyby, waving below at the problem, appreciating how difficult it is. And for one of them, we're going to go and geek out and look at some of the math and technical details. Right? So let's start with the very first one. So here's the setting, back to our simple example. I have 2 cars, car A, car B. They are operating in different cities, different time of day, different routes, or maybe they are the different versions of software of the same company, but they are 2 cars. And the question is the following: is car A more safe than car B? We don't have an answer for this problem. Partly because defining what safe means is very subjective. There's no common consensus on what safety means. For example, the industry will tell you the safety comes from how many miles you drive and what you tell the world about it. So it's kind of a voluntary self-measuring stick, which I'm not, criticizing because it has been shown to be not effective and it can be gamed. But really, this shouldn't be the standard on which we objectively measure safety of autonomous vehicles. And so data points like disengagements per mile, total number of miles driven, they are indicative of progress, but I wouldn't say they're necessarily indicative of safety. All miles are not equal. Right? If you drive in a busy street with unexpected situations, and trust me, I grew up in India, I know a thing or two about unexpected traffic. That's different from driving in a structured California 101 freeway traffic, which can have its own edge cases as well. So how do we answer this? We don't have an answer if we have 2 vehicles which is safer. That seems to be a big problem. And I would say in order to attempt to answer this question, we first need to answer another question, which is, if I have to compare 2 vehicles, let me at least observe them under similar traffic conditions. That would be an apples to apples comparison that, okay, 9 out of 10 vehicles did this vehicle did something else, 100 humans did this in the same situation. And then I might be able to statistically say something about the safety of this system. So this is the question that I have chosen to answer, and not the first question, because I feel this is a precursor to answer the question. So I'll give a very simple example. You have a company, fictitious self-driving company, and they have their fleet and data set of how their car works. And we want to compare this company's car against other companies which have their own fleet and their own reference data sets. And so here is one very simple toy problem. If I pick some interesting scenario, I want to see how Driftic handles tunnel traffic. Then given this example of a reference, you can think of a reference as the safety operator intervenes and that entire time volume of data becomes a reference. So some reference, given that, can be automatically find similar situations, traffic situations in the other data set. So that you can now start comparing how all these vehicles operate under tunnel traffic. And so to do this requires some careful embedding and careful crafting of how to formalize this problem. And that's what we have tried to do. We have to define a space over this hyperdimensional exploration that I showed, where we can create an embedding of a scenario. Given data, I can project that into some point in my space, in my embedded space, in my latent space. And then I can define a distance function over this representation of the traffic situation. And then if I have this distance function, I can talk in terms of similarity or a vicinity of a scenario to figure out what situations look alike. And so this work is called scenario to vector. It's an attempt to automate extracting a description language of high-dimensional traffic situations for any kind of autonomous vehicle. And the goal is really the following. Here, the example of the data from the vehicle is just video. It doesn't have to be just video. It can be video plus LiDAR plus your favorite sensor. And so the goal is, given these 2 traffic situations, are they similar or not? What would a human say whether they are similar or not? Or how would you even find that they are similar? And I'm not talking about similarity in terms of pixel space. right? A left turn is a left turn no matter what time of day it is in the vicinity of other parked cars or moving cars. So we are really concerned with measuring this action of the agents around us and not just the scene geometry of what other agents are present in the zone. So fast forward, we came up with a very open framework scenario description language, which looks at the world in form of actors, which are agents, scene elements, so there is an intersection or not, what kind of road geometry there is, and the actions attributed to each actor. And there is precedent for this sort of work in open scenario and scenic and many other attempts. So this is not the unique contribution. The contribution is I want to be able to learn these scenario descriptors from real data, right? So, and you can imagine this kind of a spectrum where you can have very, very refined analysis of the action of these actors, or you can compose them that, we don't care about the aggressiveness of the turn, they're just right turns, or well, all turns are really just some kind of turns or merges, and eventually you can be very, very coarse-grained as well. So depending upon what data you have, you can choose where you want to operate, but the name of the game is, can you automatically extract these interpretable scenario descriptors from video data in this example? And so the way we have gone about this is there's a very interesting data set called BGDX. And the interesting bit of that is for every video, it has been captioned by a human annotator. And so you can use this human caption as a alternate means to extract the ground truth. And so we have a bunch of papers which tell you, given the caption, how do you figure out the labels for this automated extraction, which can be cast as a supervised problem. And then you can attempt this automated SDL prediction yourself. And so I'm going to be intentionally quick here because I want to kind of, just give you a flavor of the kind of things we have done. We have tried many approaches, but this video-based transformer approach seems to be very, very effective at predicting the correct ground truth labels from just this traffic data into this scenario embedding. And we have shown in our work that using this embedding, you can look at two examples. So let's take the previous example. You can convert both of them into their interpretable vector and then compare the similarity in vector space to kind of solve this retrieval task of similar traffic situations. And so the early results show that there is some merit to this work. It's not super accurate, but it performs better than pre-trained models or any kind of off-the-shelf convolution-based feature encoder approach.
So how does this compare to like the scene captioning? Is it like scene captioning, but for the other agents?
So it's similar because scene caption is trying to generate a natural language view. So you could take a situation, caption that into a scene, and then go from a scene to sentence to vector kind of a thing as well. I think the difference here is I'm really going after these actor, action, and kind of the scene elements directly from the data. What we are trying now is the reason why we think this doesn't work well is because at the end of the day, we are trying this very simple supervised approach. And I think we are wasting network capacity on actually trying to solve perception as well, because it's learning these action sequences over video, but it uses a lot of the network capacity just to do that problem before it can do the feature extraction problem. So I don't think this is the best way to do it, which is what we are trying now, where for most autonomous implementations, you have your data, but you already kind of parse it into this latent space. And if we can operate in this low dimensional representation of traffic and still be able to generate a vector embedding over which you can define distances that we have described in our papers, then I think this will perform much better. And that's what this work is currently headed towards. So we look at trajectory data now, not perception data. So you can think of this view as after the perception has done its job, this is what you are left with, where every agent is, how it is moving. And you can look at their trajectory and try to infer the actions of turn, merge, pass, slow, left, right, all that jazz, just in trajectory space now. Okay, so that is essentially the high-level problem. I have glossed over many, many details of this problem. Yeah.
So this left turn, right turn, aggressive, not aggressive, is that tokens you have in your console?
Correct. So they are treated as tokens.
So you have a quite limited amount of tokens in the transfer.
Yeah, they're only pertaining to the domain knowledge of kind of traffic at hand. But I mean, we don't limit these tokens. The use of the tokenization is only happening when we extract the ground truth from the natural language caption.
Okay.
Right? This transformer business is simply treating video frames as the different tokens of this process. So it's like a video transformer. If you're familiar with the things like Vivid or any kind of action prediction transformer,
Okay.
that transformer doesn't go into language first. It's tokenized over image patches. Yeah. All right. I know it was a rapid fire, but in the interest of time, I'm going to jump on to the other problem. Okay, so while I did answer how you measure safety, I'm just telling you have to answer something else before you can measure safety. So let's go to how do you improve safety, right? And here's an idea. Going back to our example, here the idea is let me try to, if I'm given an autonomous vehicle that can only do so much testing in the real world, can I use simulation to explore this high dimensional space effectively before I try to deploy it elsewhere? So this is hinting upon looking at improvement in autonomous vehicles from the perspective of efficient testing. But I don't just want to simulate arbitrarily. I want to generate some rare, meaningful situations which really test the underlying motion planner or perception algorithm of my car. So I'm interested in scenarios where the autonomous vehicle fails. That's the goal of this search. Can I find situations in simulation so that I can find those failures, address those bugs before we deploy them into a real city? And we want to do this automatically. We don't want to have engineers figure out creative ways in which vehicles can fail. We can guide that from real world failures, but the search should be automatic and efficient. And so this is the role of, this problem is in the scope of simulation-based testing for AVs. There have been many attempts. People have handcrafted some very interesting photorealistic edge cases, not scalable. You can replay logs in this latent space and also mess around with the trajectories of other traffic. And so there's a lot of potential, a lot of work has been done in building good simulators. So let's leverage that and try to solve this scenario generation, adversarial scenario generation problem. And so here is the key idea. You have a simulator, pick your favorite simulator. In this simulator, you have an autonomous vehicle. And you can use some off-the-shelf open stack to let it drive, or you can do your own secret Docker image of Waymo stack if you have access to that. So you have this autonomous vehicle in the simulator. Most companies will create scenarios and then try to improve their autonomous vehicle through some kind of reward shaping or scenario-based testing. And I think there is merit to that work, but what we are doing is a little bit of the inverse of the script. I say that I don't care about your autonomous vehicle as long as it runs in the simulator. I'm going to control all the NPCs in the game, all the traffic agents. And these agents are going to get rewarded to try and cause a crash with your autonomous vehicle that you control. And for every crash I can find, assuming that it is salient, means it's a realistic thing. It's not some arbitrary teleportation or when the AV is not at fault, which is a difficult problem to nail. But this property where we control the other agents to cause a crash is what is called automatic falsification. So you get rewarded to try and cause a crash, and every crash is kind of a falsification event that you have discovered in the space of this autonomous vehicle. And let's say you keep doing this falsification, you generate a library or a policy for your adversary that can falsify this ego. Then you can retrain your ego against this grandmaster, which is able to defeat you. And this loop of retraining is what I call safety hardening. It's not a guarantee. But if you do this iteratively, statistically, against better and better adversaries, you will improve your ability to drive better in situations where others are trying to inhibit your progress. And so this framework is what is called CRASH, which is adversarial RL for causing these literal crashes and enhancing the safety by this soft process called safety hardening. Again, let's go into the racing mode and speed through very early toy problem attempts at this problem. This is really the newest problem I have been working on, and all of the other stuff I will talk about. But we started very small. We look at this highway simulator, which is open source. You can describe this simulator in terms of a very large but finite MDP with the states of every agent, their velocities, and very simple sort of action space in terms of what the NPC is allowed to do. And then you design a reward, nothing special. This reward is really the same reward as what you would use if you want to design an ego vehicle, except that now my NPCs are getting the inverse of this reward. So usually you want to try to maximize your time to collision. My NPCs want to minimize the time to collision. So you can think of them as they will behave like honing missiles to the ego vehicle, subject to the dynamics of the simulator. So there's some dynamics to how fast you can change the lane, how fast you can accelerate and slow down. So all of this is preconditioned to the realism of your simulator, but given that realism, you can design this very simple time to collision based reward, which will give a both continuous reward and a discrete reward every time the NPC is able to cause a collision with the ego vehicle. And so we tried a very simple version of this where the NPC's policy is essentially a DQN network. So you can train it over multiple episodes and it can accumulate reward. And based on some ego vehicle, it turns out that this can falsify and cause a crash in this very simple 2-lane geometry of the problem. So of course, can we do more vehicles, more lanes, different geometry, traffic signs, crossroads, all of that is on the table getting looked at, but the early results are quite promising. But this is still just a falsification. This is, I would say, relatively straightforward. And I think there's been other works in this problem of importance sampling and choosing what scenarios to model, which touch upon the same key ideas. The new part is this safety hardening. Okay, and the idea is I have this ego agent, which I use to train my adversary. So the ego was sort of frozen when I trained the adversary. Now let me use the adversary in a regular simulation, in like a forward reinforcement learning, and train a new ego with this better adversary. And then freeze this ego and train a better adversary. And then keep doing this iteratively. This is kind of this fictitious self-play idea behind some of these very powerful results in StarCraft and AlphaZero. And so we are trying to see how well some of those ideas apply to this problem. And it's not a given because it's a different reward mechanism than in these games. But there are many clever tricks you can do here. For example, rather than training against just the most recent adversary, you can train against a pool of all previous adversaries. You can even use some weighting mechanism to gauge the strength of each adversary and then sample in some probabilistic manner, which is called prioritized replay. So these prioritized replays is not itself the novel bit. The novel bit is the setting of the problem where we are using this gaming setting to define when does the adversary win, when does the ego get rewards because it avoided a collision and things like that. And so in my view, this is sort of the stepping stone to the literal chess equivalent of this version, where the test of a self-driving algorithm and simulation will be, can you defeat this adversary grandmaster, the Magnus Carlsen of causing crashes? If you can beat them, then we have some faith that you will be able to deploy reasonably well in the real world. There are many challenges to this. We want these crashes to be realistic, which is a saliency problem. So, is it my fault if somebody shunts into me from the rear in a traffic collision? Could I have done something to avoid that? The easiest behavior is the adversary crawls up to just to be adjacent to you and just kind of yanks the steering wheel into you. So keeping that saliency is still an open problem, and we have some ideas to look at real world failures and make sure that these adversarial attacks cannot depart too much from real world human trajectories during crashes. So you can regularize this search further. All right, let's move on in the interest of time. Let's come to this problem. We're talking already about these unexpected situations and how to generate them. So might as well talk about how to handle them. And here is where the connection with racing became my choice or crazy idea or hypothesis, what you may want to call it. I put forth this idea that can we use racing as an arena to learn in this motion planning space. I'm not really, I concede that racing doesn't look like driving in the real world. These cars are also specialized. But can we learn these high-speed, close proximity behaviors from expert examples with the hope that some of that, not all of that, some of that can help handle these dynamic situations in traffic. Every single time, it's not always the best strategy to hit the brakes. Sometimes you can just kind of, find your way out of trouble, as they say. So this was the very high level hypothesis, the career proposal, as Rahul said. Can we establish this connection? And so in the past few years, this has been a big thrust of the research that my group has done, starting with a very simple thing. How do you even do this without a race car? So how do you train this unique expertise? How do you observe racing drivers? How do you look at their data? And for here, what we did was, rather than reinvent the wheel, we essentially built on the shoulders of giants. So this is the Formula One game from 2019. Now it's even better. And that's the real footage from the real race. And if I had swapped the logos, I think you could still tell this is still not maybe outside of the uncanny valley, but it's down close. So the photorealism is great. The physics of these games is so realistic that during the pandemic, Formula One drivers were racing in this game because they felt like it was as good as racing a real Grand Prix. And so what we did was we looked at this $39 game and we converted it into a closed loop ROS simulator, where you could get the data out of this game as a ROS interface, and you could do whatever neural network or classic closed loop control you want to do. And with the Python API, you could control this agent autonomously, enabling you to test some closed loop performance in this game. So this really became the playing field where where all of this research stemmed from. And as you can imagine, with something like this is not really a simulator because it doesn't have sensors. It just has this television broadcast camera, which we treat as a camera. But even with this, you could do some low-hanging fruit, like try end-to-end stuff. Right? So you just train a neural network to look at the image and directly control the car. Something which is called pilot net approach that doesn't seem to work at all for this kind of racing situation. And this is after spending a lot of time tuning these, trying to replicate how people have done this for smaller examples. So you could add some recurrence to this neural network, end-to-end network, by giving it some context of a history of images, asking it to predict a few sequences in advance, and that still drives like an anxious driver, kind of like what would happen if I were to drive F1 car and it will just crash into the wall and not be able to recover. So a better idea is to not try to predict control directly, but to try and predict the trajectory and then pass that to a low-level controller. Because it's a much more well-posed problem than trying to directly predict from image to a steering angle, because same images can have different steering angles. The same driver goes over the same part of the track again and again, but their steering may be different every single time. So here's what we did. We cast this problem as predicting a sequence of waypoints, which has also been tried in the literature. That works a little bit better in the sense that if you predict pixels to trajectory waypoints, at least your car is now able to make a lap in one piece, but it cuts corners. When the scene becomes all gray, then it doesn't know what to do, what trajectory to predict. Still too brittle because of supervised learning. And part of this brittleness is that predicting raw waypoints is very, very inefficient. Because every waypoint you are predicting X, Y, Z, the track is 3D, and heading and velocity at which the car should operate there. So there's too many things. And you're predicting in a horizon where you're predicting hundreds of 5 or 6 of these things. So 500 numbers have to be predicted correctly for this to work, which is not easy. You can get 1 or 2 wrong and then it will not recover. So the key idea here was, and this has been the backbone of all of my research, is let's not predict absolute waypoints. Let's treat them as Bezier curves and only predict low dimensional control points of the Bezier curve. So we represent trajectories as Bezier curves. And now we only have to predict the control points of the curve. And you may have forgotten what a Bezier curve is. It's basically the red line is the Bezier curve. It's uniquely defined by the gray control point. So an infinite dimensional curve is defined by a finite set of 5, 6, depending on the order of the curve, number of points. And this is just a little bit trivia for you that Pierre Bezier, who invented Bezier curves, he used them to model the body shape of Renault race cars. So in some poetic manner, I'm bringing Bezier curves kind of back to racing, which they were meant for. So you have this low dimensional representation in form of a Bezier curve. So now you can use all the mathematical properties that they're continuously differentiable, Bernstein polynomials. They have very good endpoint interpolation properties as well. So now our problem is, let's output a Bezier trajectory and let the low-level controller follow that trajectory. And this is a lot more stable than predicting raw waypoints. So it doesn't cut any corners. It can make progress in the same track. So previously we were going off track here. Now the car can kind of resemble or drive like the examples of the humans on which it was trained to drive. And so this entire framework is called Deep Racing AI. It's open source. Anybody can download and buy this game. It now works with the Formula 1 2024 as well. And you can pick your favorite algorithm and your favorite track, and it will support all of this, all of the parts. But this is not enough. This is just supervised learning. So it's a good starting point. It's a good test bed. But really, we want to solve how do you handle these situations. We want to make progress towards multi-agent, not just single-agent cars. So what we want to do is not just predict what the expert would have done. We want to synthesize the right thing to do, the optimal thing to do. And that was this work called differential Bayesian filtering, where the idea was that using supervised learning, we can already predict this Bezier curve, like I have shown you, and it works. But your performance is going to be limited by the situations your expert, my student Trent Weiss, has been able to show the car. You can never exceed human level examples. So what do we do? Right? How do we overcome this curse of supervised learning? And we can't do much here. We can gather more data. So we should do something in this representation space. And so here was the idea. And this is really the idea behind the sequence of at least 4 or 5 recent papers, that instead of just predicting one curve, a Bezier curve, we are going to learn what are called probabilistic Bezier curves. So the curve itself is not what we are interested in learning. I'm interested in learning the distribution of trajectories that are possible on this racetrack across all the examples. With the idea that once I have learned this distribution from supervised data, I'm going to sample from this distribution, assign some score to that sample, and if necessary, resample, assign a score, resample again. Things that we should seem familiar to us roboticists. In other words, given this distribution, let's say I have a candidate trajectory, I can just say this is a bad trajectory, it's going out of bounds. I can assign a likelihood score to that, probabilistically. There might be some other weird trajectory. I would say this is not even kinematically feasible. It exceeds the lateral capability of my F1 car. I won't allow it. Score is low. And if I do this iteration, this Monte Carlo sampling, eventually I can converge to some kind of optimal trajectory, which doesn't change from one iteration to another. Right? So this is what we are doing. We have these likelihood scores which capture what we want the trajectory to be rewarded on. And by this iterative sampling, we can generate the nominal trajectory in this. This is a slowed down version of what the algorithm is doing behind the scenes. It's doing this iterative sampling until it finds the trajectory which doesn't change. And so you can think of this as running like a particle filter, which is also this sequential reweighting and sampling and resampling, but every particle is a trajectory from this distribution. And so there is a chance that you can sample a trajectory which was not even present in your real original data. Yes, you are limited to the distribution of the data, but the outcome of this process is that you can generate some posterior curve in this Bayesian manner that can actually outperform all of the data that you use to train it. because it's using probabilistic measures to sample and rewarding these away from the mean samples through these likelihood models. So not quite as fast as Lewis Hamilton, but it's getting close to, some rookie level Formula One driver in the game. So there is some promise here that even using supervised learning, you can break that curse and learn in this probabilistic manner. So this is again what is called DBF, or differential Bayesian filtering. And this algorithm, like I said, is a sequence of works. The next idea was there is no need to train on images anymore. We can just literally train on trajectories. There's no need to train from pixels. So given historical trajectory, can I predict future trajectory? Well, this is trajectory prediction problem, but you can again use Bezier curves for that. So using my deep racing framework, we used to log into motorsport, esports series, and just log everybody's data without them knowing this. I don't know if there's legal implications of that when I say it on record, but that's what we did. So we have millions of trajectories of esports drivers and data from the real world that we have trained on, essentially to show that you can use this DBF mechanism also for trajectory prediction. You can predict that what are the various possible outcomes of my opponent right now in this game. And so let me kind of maybe go to the punchline. The reason why racing prediction is different from ordinary prediction is the velocities tend to change very, very fast. The racing dynamics, these cars can accelerate and decelerate far more superior than any road car. So your trajectory prediction mechanism trained on road traffic or road data will not work for predicting the trajectories of racing cars. So here is that sample. This is a long trajectory, about 300 meters long, several seconds. And you can see the speed profile changes from very fast to almost breaking into that corner. And so this trajectory prediction idea is using the key that everything is represented essentially as a Bezier curve. That's the one take-home message if you want to recall. I don't want to even explain these plots because they're pretty dense, but everything is a Bezier curve, and even the velocity that you're trying to predict is something called a composite Bezier curve. This is the paper which will be presented at, who got accepted at RAL and will be presented at IROS later this year. So this performs very, very well, even better than some of the motion transformer based work, which has been the winner of this Waymo trajectory prediction competition. But of course, that's for pedestrian passenger AVs. So they're not really one-to-one, but when you try that transformer on this racing data, it struggles in predicting the longitudinal velocity errors, because again, predicting velocity of race cars is much, much challenging than predicting their steering. And also it runs much, much faster, more amenable to running on real hardware. And so finally, what has remained is we have an ego vehicle, and we can generate its single trajectory with some likelihood. We can have opponents. We can also generate their Bezier trajectories as predictions with probabilities. And now all that remains is if you want to do multi-agent racing, you can essentially define these additional likelihoods in terms of what safety envelopes you would want to respect in the manner of a Bayesian framework. And you should be able to adjust this maximum likelihood trajectory accordingly with that tool. Right, so this is exactly what is happening now with multi-agent racing that my group is working on. All right, almost at the finish line. Let's talk about the last problem. We figured out how to generate trajectories in some clever manner. Now, how do we follow it? Why is it so difficult to follow trajectories? It's not in general. You can use pure pursuit to good effect, simple, fast algorithm. But for a race car, the dynamics is painfully complicated and nonlinear. We have to estimate slip angles for which we need data from the tire manufacturer, not easily available, to look at how to, what is my longitudinal force that drives the car. I really need to put the car on a dyno testing, which we did for our race car, get the torque map of this testing. Too expensive, right? We need something that can get us this accurate level, but without painfully going through the process of these hard experiments. You can do this if it was a one-off car, but in practice, you need to be able to come up with methods that can learn the physics accurately without this cost and time prohibitive manner. And so there are two works that I have done, and this is all I will talk about that. One of them is using the idea of physics-informed neural dynamics modeling, where the idea is the neural network is going to estimate some of these coefficients. I'll give you an example. Estimating the moment of inertia of a racing vehicle is next to impossible because you really need a CAD model to look at how the weight is distributed around the CG. But you can guess. You can guess that this vehicle weighs this much, this is the dimension, my moment of inertia should be in this range. So this physics model is trying to estimate the parameters of the physics equation as the output of the model. These parameters are then passed through the same ODEs to generate the loss. So in other sense, the internal estimates of the model have to respect the underlying physics that we want the model to respect. And we put some guard functions in these layers to make sure that the parameters are always in their respective values. They adhere to known physical values. In this other effort, the following idea emerges that all models will be wrong. Let them be wrong. Let's try to learn a different model to predict their correction on top of the simpler model. And this work there's many sequence of works which has happened here. Even with F110, there's a paper called Behl's race. And the key extension and novelty with this Gaussian process learning is that how do you know what kernels to use? Right? You are basically replacing your model choice with like a burden of figuring out what kernel to use. So just learn the kernel. And so we've come up with this new method called deep kernel learning, where you can correct the predictions of a simpler model, but instead of you handcrafting a kernel, you will learn the kernel from the data itself. And this actually has some promise that some version of this can run online on a real race car as well. All right, so these were the 4 problems. And the reason I kind of stopped here is I want to just take 5 or 7 more minutes to talk to you about. I've been fortunate enough in my program to realize some of these problems on the real race car. I want to just tell you the story of this team, not necessarily repeat all of the algorithms and show you how well they work or how well they don't work on this team. And really where I started was on 110 scale. This is a picture from my lab in 2019, where we had a fleet of 20 F110 cars trying to do this multi-agent planning on this 110 scale. And later on, we were able to scale from this 110 scale to 1:1 scale through the Indy Autonomous Challenge. And over the years, my team has grown from a mere me plus 5 of my students to now more than 25 students, including undergraduate, master students, and my PhD students as well. And so we sort of raced through the pandemic. I said the same thing during the class in F110 today, to qualify and emerge as one of the teams in these 3 years of hackathons, monthly hackathons, to get to design and race this real world full-scale autonomous race car. And this race car has all the real sensors in terms of 3 luminar lidars, which give you 360 field of view, front-facing radar, side-facing radar, medium range, long range, different redundant GPS units. And so this was a dream come true, really. And our very first race was held at the Indianapolis Motor Speedway, where my team, along with some of the competitors from Europe, Korea, and other US universities, we did our very first race, which was just time trial. I'll play a little clip of what that looked like.
Nice smooth launches that you see. And additionally on the engine, we wanted to make sure that it idled at a very low speed.
So much to be proud of.
Oh, absolutely.
Right, so most autonomous vehicles on a good day will go 55 miles per hour. But this race car exists the pit lane at 90 miles per hour already.
Even when
And this is
Scale
fully autonomous.
autonomous
There's
race
no
cars on real-world racetracks, and his UVA program has managed to do exactly that.
yeah, Madhur had
Experience with that, certainly.
So in this format, the car is figuring out when to do a performance lap, when to slow down and do warm-up lap. And you are just running by yourself, so the competition is basically how fast you can go. And on this cold winter morning, we emerged as the fastest American team in the competition. A team from Germany went ahead and won this competition. And I know when you look at this, it looks pretty good, but it also, you can't help but become this thought that this is just one car. So how difficult could this really be? I mean, I know it's engineering, but is it really difficult And I'm here to tell you it's very, very difficult. There's many things that can go wrong, right? So you can lose track of where you are and then just go off track, and that's a localization failure. So you have to kind of have the foresight to bake and have redundancy for that. Another kind of failure is your controller is unstable. You're not able to steer properly when you amp up the speed, and you can kind of just shunt into the wall. Another failure is that you actually tap the wall here. The car should have realized something has gone wrong, but it doesn't. And so now physics takes over and it will eventually just, collide. So you have to have safety and failures built into these vehicles. And so the next race we had was, let's have another car and overtake this other car with a set of rules. And this was an overtaking mechanism where you had racing flags, radio flags, and we set up this pit lane. And we had this, head-to-head competition. And so here is how that went when we went to CES in 2022 at the Las Vegas Speedway. This is what a typical racing event looks like. Most of the time we will be in the garage, kind of tweak our algorithms, making sure everything is fine. And then once we are happy with the testing, we will roll out the car to the track. This is what it looks like for us. We are mostly staring at the monitor because we are not really controlling anything. And we are testing whether the car is doing what we expect it to do. And so on this race, we were overtaking the Italian team one day before the competition in practice at 125 miles per hour. So this is from the vantage point of the opponent, and you will see my car does the overtake. And then it tries to kind of close the door on them, and now you realize the cost of luck in this case. So it was one of the worst crashes that the competition has seen. The entire left side of the car basically got destroyed. So pretty expensive crash, but at the same time, we learned tremendously that we had to overhaul every single line of code that was behind this mechanism of overtaking and lane switching. And so I really love this picture where my students are holding one crashed part from that crash, because we saw the glimmer of hope there. So over the past 3 years, we have raced across prominent racetracks all over the country at various speedways. And honestly, the story I really want to tell you is one of failures, because despite our success in the first race, top American team got all the funding and the media visibility going. The next 2 years were painful. One, we crashed out in 2022. In 2023, we could not even qualify to race on race day, because we were doing this overhauling and really starting from scratch. No more pure pursuit. You have to build a model. You have to learn the tire dynamics. You have to do it properly. There's no shortcuts. And so we gave up. A lot of these times we used to show up and it was frustrating because we never be able to even race on race day. Until this year, when we went to Vegas, it was a tough ask because we only had 3 practice days before there was a dry run and eventually the race day, and we were not even qualified coming into this race week. And so I will close off by just describing to you what happened in Vegas. Will not stay in Vegas. I want to share it with the world. So here is what it means to qualify. To qualify, you have to show that you can autonomously go up to 120 miles per hour, slam on the brakes and demonstrate an emergency safe stop. In the case that race control has to tell your car to stop be safe. Not only that, you have to overtake this virtual opponent, this ghost opponent. It sounds like science fiction, but that's what you have to do on track. And then really the real test is, can you overtake a real car and not just these ghost opponents? And going into this week, this year, I think we were kind of here. We had never done any of these 3 things since our crash in 2022. And so the very first day, because of our simulation efforts throughout these 2 years, this is the very first run of our car going 120 miles per hour on day 1. And so once the steering looked pretty stable, we request a red flag to test this emergency stop. And this is literally what we see. That's why I didn't show you the car. I'm showing you what the team sees. We're looking at this monitor.
Sending a red flag.
10 of us.
3,
that yellow square is going to turn red, and we see the velocity drop because we can't even see the car. It's somewhere else on track. That's how we know it's about. So this is what real racing feels like. We ticked off this qualification on the first day. The next day we had to overtake a ghost obstacle, and that's what this looks like. Your race car is going to overtake this virtual opponent. There is no real car on track, but it's going to try to demonstrate that if there were a real car, I can plan around it and still execute this maneuver. So you can see the car will veer out, follow this prescribed plan, which is getting generated. In fact, these trajectories are Bezier curves in our current planner. So we are using some of the research, not all of it, but some of it. And then it can pass. And so we check off another qualification attempt. It's a miracle, to be honest. I was like, what is going on? 2 days and we qualified one after the other. We basically went from unseeded to top seeded in this year's competition. So when everything clicks, it's kind of vindication of all the effort you have put in. So the third day, we had to gather perception data. We never thought we would get this far. So all we did this entire day was just slowly coast with other dancing partners, not doing any crazy overtakes, just making sure we gather enough data so that we can see them through our LiDAR sensors. And that's what we do on the dry run.
So you're detecting opponents just with the LiDAR, no camera?
No, it's a fusion of 4 different things. So there are multiple LiDAR pipelines. There's a camera pipeline and there's also radar detection, and we fuse them together. And so the real testers will it work on when it matters. So this is like a dry run, and you can see our car is able to track the opponent, the German team, autonomously. So we are not doing anything, it's maintaining its speed. It's doing what is called adaptive cruise control in other sense. So that's what we need. If we can track them, then we can overtake them. And so this is a low speed, one of the first overtakes that we've ever done. Nothing remarkable. All this is like routine for many of the European teams, but for me, this was 3 years worth of effort after we had crashed and overhauled all of our stack. And you can see it tried to go on the outside, and then it figures out, no, there's no room there. I have to come back in and accelerate and complete this overtake. So I'll close off with really replaying how the race day went, and then we can call it off. It's almost the end of time. So on race day, the game is this game of chicken. You have to overtake an opponent, and then they get to overtake you, and you overtake them, and so on and so forth, until one team decides, I don't want to push my car to anymore. So here is our car overtaking the MIT team when they were going at 80 miles per hour. So this is kind of similar to what we already did in practice. So the next round, they are going 100 miles per hour, and we have to try and overtake them again. So this time we will speed up to 150 miles per hour, right there. And it's their turn, and then they also succeed in overtaking us. So we say, let's go even faster. So now the MIT team is going 115. And you will see in this overtake, if you can listen in. That's what this autonomous car sounds like when it gets into 6th gear. And it hit 143 miles per hour. This was great. And then the MIT team couldn't overtake us, and we advanced into the final round. No, 143 was what our car decided would be required to overtake a 115 mile per hour car. This is the final, so we were top seeded, so we had to overtake first. This time, Toom is very dodgy. They move around, but our car decides to overtake in the middle of this bank turn because it's the best opportunity that they present with their race line. It's not like always that you will overtake at the same part of the track. It's open season, wherever the algorithm decides.
They have to stay at a fixed velocity.
They have to hold their velocity. This is the shielding rule to keep everything safe. And now it's their turn to overtake, and I was ready. I was like, let's go to Milo 160. And so they line up for their overtake.
You can move.
You cannot. You have to pick a race line, and you can choose a different race line every lap. But once you have a race line, you cannot leave.
Oh.
So when they were about to overtake us, our algorithm decides to just speed out of this overtake.
Wow.
It doesn't yield to them. So you will see that my car just decides to all of a sudden go to 150 miles per hour. They were,
That's the way to do it.
so they were like right next to us, almost ready to overtake, and then you see our car decide goes down none of that. So we know exactly at that moment, I knew when I looked at my student what has happened. Our cost tuning was such that we were predicting somehow that Toom is going to collide with us in a future instance. And the best thing was to have this evasive maneuver. So, but this is a rule infringement, and the round had to end, and we secured a second place in this Indy autonomous challenge. So there you go. This is what the journey of autonomous racing has been. Moving forth, things are going to get faster and better from here. My next race is going to be back at Indianapolis Speedway, but this time, for the first time, we will try to have 3 or 4 cars on the track at the same time. The original goal of using racing at this multiplayer arena. And then next year, we will transition from road courses, from oval tracks to road courses, when we will race in Italy at Monza. So autonomous racing is very exciting field. And the genesis of this entire domain is in some sense in this building where the first ever F110 car was run. But in my mind, we are merely getting started. We're nowhere close to what human drivers today are capable of doing. If you look at the career of a racing driver, they have this mental model. They've been racing since they were a kid. They can assess situation and risk, and many of them will tell you, I drive with the feel of the car. I know when I'm exceeding the limits or close to exceeding the limits. Autonomous racing has had its own progression in scale. We have different scaled vehicles, but we want to also match human capability in terms of what the drivers are able to do, and we are long way from that. Today, if I had to pit my Indy autonomous car against human drivers in the Indy 500, we won't even qualify. Their average speed is 230 miles per hour. And the fastest Indy car has ever gone is 192 miles per hour on an aircraft track, not even a racetrack. So the true speed is that we routinely see is 170, 160 miles per hour. So that's it. I don't want to keep you here any longer. This is what my research is about. Hopefully, it has brought forth to you some very deep, challenging problems and some of my attempts to navigate these very difficult problems. But the key is to always keep them exciting, because then you will be motivated to work on. I'll stop here.
Thanks for the awesome talk, Madhur. I think we can maybe take a few questions, even though we're over time, but if folks need to leave, that's understandable. But does anyone have a question they'd like to ask? In person or online? Maybe I'll ask a question to start while people think about it. So I'm curious, like, what kinds of problems you think are best suited to the scaled cars versus the real cars? Like, what is the limit of what do you think is the most, the very edge of the limit of what you can do with the scaled vehicles?
I think the problems I wanted to originally solve, multi-agent racing, you can do that with scaled vehicles as well. You are restricted by perception a little bit, because to make it realistic, you sort of have to scale the world down, or you need to add enough sensors where you can see all around you and not just what's in front of you. But honestly, solving multi-agent and demonstrating multi-agent would be much easier on an F110 car. And we'll find out in October this year, one way or the other, whether racing 3 cars or 4 cars was a good idea. But a lot of these fundamental problems you can do in planning on scale vehicles. What you cannot do is where all the real world matters, things like tire dynamics, aerodynamics, like designing these. If you really, your interest is in the modeling part or the control, how do you control a robot going 170 miles per hour? Well, simulation doesn't do it justice. We tune the simulator, but we spend some track time to dial in our setup, dial in all the parameters. So that is difficult to scale. I think simulation is a good proxy. And I didn't say this at all, but one of my attempts in order to basically facilitate others being able to replicate this work is that we've released all of this data from 3 years from the Indy race car. So even if you don't have a race car, you don't have a scaled vehicle, you can look at all these different racing situations at the same car at different speeds, annotated ground truth GPS position to still solve these problems. And this is something I learned from F110. The reason why it's so successful is because of the community and this kind of all the people who are solving with this common mission. So it shouldn't be limited just because we don't have access to a full-scale race car. And that is some things you can only do with a real car that you cannot replicate in simulation.
Thanks. Yeah. Other questions?
Yeah, has there been like ever like a problem with, I guess, the reality gap, or like when you're moving from simulation to reality, has there ever been a problem?
Yeah, every single time. Here is a better answer than I can ever give you if I can find it. Maybe it's not here, but so we tune our model predictive controller, which means we have to tune the tracking costs versus the control effort, and that's all done in simulation. And we use a variety of different simulators. I think I have just a quick tidbit about what simulators we use. It's like at least 4 or 5 different kinds of simulators we use based on like a very simple motion planning simulator all the way to multi-body physics, where we can simulate the suspension geometry, how the wheels are turned and all that stuff. But none of that maps exactly as prescribed when we are on track. So on track, we have dialed in and we have looked at specific measures. If our steering effort is jittering, or there's an algorithm that detects the jitter in the steering. If it is outside of what we expect in the simulator, then we know it's time to bump up some costs. So many times over lunch, I was describing this as well. Over the radio, I am in the chase vehicle, keeping an eye on the car, telling my pit crew over the radio that dial up this control effort, the steering looks unstable, telling them how the car reacts. Because the data we stream over the radio is not real time. It's like at 5 hertz. So it doesn't tell you exactly. Only when the car comes back and we look at the real data logs, we know whether the steering was stable or not. So we almost always have to shake down the car every time we go to the track. The first 2 days are, let's just get to the baseline from where we left it. And if it's a new track, that's maybe 3 or 4 days. And then we can try our interesting, overtaking stuff. But tuning is unavoidable. So we're not trying to do some tuning on the fly, but it's mostly being done to test in simulation.
Any last questions? Check any questions?
I was also kind of curious about like edge cases. Are there any differences between like edge cases like on a racetrack versus like a car on the street where like crashes or like intersections are not in this edge case?
Yeah, there's a big difference. I think the acknowledgement here is that racetracks look nothing like real world traffic. These cars don't run anything like real world cars. They're kind of performance driven, special brakes and drivetrain cars. So we have to be very careful when we make any kind of claim that, hey, I avoided an edge case in racing, therefore I can also do this. So this is one of the problems which I think nobody has solved, in my opinion. Right? There was a promise that racing can improve regular driving, just like motorsport to some extent has led to some safety improvement in luxury cars first and then normal cars. That has yet to be shown for racing. And it's not an easy thing to show. So my bet was that this could be shown in the motion planning rather than perception. I didn't talk about perception, but there's a ton of interesting problems in perception because the camera shakes at 120 miles per hour. You have to detect your opponent. So there's a thing or two you can learn about how to do perception robustly under noise that could translate as well. But what I'm still trying to show is here is your self-driving car controller. I think this would be a great problem to show. Here's your self-driving car controller. Here is whatever you interpret to be a racing supervisor or a racing agile controller. And collectively, these both are safer than if you only had the self-driving controller. I haven't been able to show that. I want to still work on that problem. So if there's clever students here who are looking to a PhD, let's come do that together. Yeah. There's a question.
Yeah. So for your last race, where the case where your model predicted a collision and
Yes.
it had to adjust. So in the next race where you have like 3 or 4 on the same track, how do you plan to, because thinking about it logically, the chances of that occurring is more likely. How do you plan to address that?
Yeah, so what I didn't get to, deliberately chose not to get into is, even with this Bezier curve business, we can now run inside the Formula One game with 9 or 10 other agents around us. So we are already using this better prediction of our. So why is it difficult to predict? Because it's difficult to predict their angular acceleration and their yaw range. That's really why you mispredict in racing most of the time. And so the short answer is you need better predictions of your opponents, but the other mechanism is there is room to. What our planner should have done is, even if it thought there's going to be some occurrence, it should stick to the rule, the state machine, and say, let me just maintain 80 miles per hour until some critical collision is imminent. That's what was expected of the planner to do. Our planner made an error on the cautious side. It was very cautious. It thought that just because they are side by side for elongated period, there's a misprediction that eventually they will get to the race line. And so either you could slam on the brakes or you could just get out of there. Because it was still trailing us, it said, well, let me just go faster. So that's a illogical error on the part of the planner. So that is easy to fix. The real challenge in multi-agent perception will be how do you kind of make sure that you can predict everybody reliably in the same amount of resource in your computer in the same amount of time. So do you need a single model that can predict all agents versus a different model for every agent that can come and go into the field of view? We still have to figure out and try. I don't really have an answer. From the planning perspective, we feel more prepared. Our planner design from the ground up is such that at least in simulation, you can scale up to 5 or 6 agents and it will still try to do its best. But not yield like we saw.
Yeah, sorry, another question. So what I get is better predictions, right?
Yes.
So the question is now what it does with the predictions, because based on the last race, it saw a prediction and reacted,
Correct.
in my view, responsibly to move out of the way. So if you now still have better predictions, it's still a cost versus moving out of the way,
Yeah, so the reason why we moved out of the way was we did not check whether we were breaking a racing rule. So if your prediction is accurate, first of all, you would not have predicted that they will run into us. The right prediction would be that they will maintain their trajectory and then merge slowly. Right?
what
So
if that wasn't the actual case? If they were actually in a course of collision,
correct.
it would be a cost versus.
That's what I
actually-
meant by saying that you have to design, if there's a really like a critical case happening where you have to, slam on the brakes or really get yourself out of this fix. So just because they were adjacent to us wasn't critical enough for our car to react this way. So that's a logical error. And I think your real question, I interpreted to mean, how do you enumerate all such logical errors? It's very difficult, which also goes into what are the edge cases of racing. So I think there is some flavor of scenario-based testing that we have to do for multi-agent racing as well. But to be honest, we are quite far from that. Right now, we are just trying to put the pieces together where can you detect more than two vehicles and plan a trajectory in vicinity of two vehicles when they are expected to follow rules. A lot of this is also rule design. And there's no prescribed rule book for autonomous racing. So we, the teams, are collectively designing the rule set for the sport. And so we weekly brainstorm in technical engineering meetings what the rules should look like for multi-agent. Should there be a radio signal which tells you to move out of the way of a winner, like in real racing and things like that. So it's an exciting moving target where there are more questions than my ability to answer them.